Okay, so the light at the end of the tunnel, we are nearly done with all the instructions for the 6502 emulator, apart from break and return from interrupt. So break forces an interrupt and RTI returns from that interrupt, or from any other interrupt actually, but it can return from an interrupt. I might want to do both these together because I can't really test RTI unless I can actually have an interrupt, and seeing as this instruction makes an interrupt for me, then I suppose I should do that one first. So yeah, this forces an interrupt. So this is an instruction that actually causes the processor to interrupt. And what that does is it puts the program counter and processor status on the stack. And then it loads the address that's stored there, which is the reset vector or interrupt vector. And then it loads that into the program counter and sets the break flag in this status. So effectively what you're doing is you're storing the state of the processor, you're moving to a new place in the program, you're going to do something, and then when you return from the interrupt, you put all that status back, and it's like nothing ever happened. So that's really what an interrupt is. It's like stop what you're doing, do something else, and then actually return to what you were doing before. And this is just an instruction that forces that. So, oh look, and it's the 00 opcode. So finally we'll have an instruction 0. So you can see that's one of the things. I think that's maybe there is some kind of hardware reason why they chose 0 as the actual value for this. I think it makes the hardware design simpler. But now when we initialize all our memory to 0, if we actually start executing the 0 in memory, it will actually force an interrupt now, which is not necessarily good or bad, but it's just the way the processor worked. Let's get on with that. I don't know whether to put this in a new file. We did put NOP in here somewhere. And that's they're listing these as system functions on this website. So maybe I'll put all these in one file, including NOP, because NOP's just stuck in some other file somewhere. It's stuck in status flag change tests. So I think I'll move NOP. I'll make a new file and I'll move NOP out into there as well, and then we'll put the rest in that. So there we go. So I've just made a new file for these unit tests, and I've called it system functions tests because that's what they're called on this website. And I've just moved NOP into there. That gives us a space now where we can move on with the break function. So we don't know what this is going to do just yet. BRK. So it's going to be BRK, and it does, I believe it does, yeah, it's got no other parts to that instruction, it's just that. It does take 7 cycles, so it expects 7. There we go. And then we now have to work out what do we expect at the end of this. We will need to put some other data into memory to get this to work. So one of the things we need to do is we probably want to put something in the reset vector here, which is a FFE the very end of memory. That's where we put the address of where we want to jump to in memory. So again, this is little endian, so let's put 8000 in there. That's just a nice address to jump to. Afterwards, we would expect the program counter to be 8000. So that's one thing. What else do we need? I mean, we could just test that in there for now. Maybe just do that one test on its own. So break will affect the program counter. Break will load the program counter from the reset vector. Are we calling it the reset vector? The interrupt vector. There we go. So I think that's, yeah, that's a good start, I think. So let's just put that instruction in. And it's 0. So that should compile should give me my one test. Instruction 0 not handled, because this time we used to be saying that a lot when I went to a funny place in memory, but now that's going to change soon because it's going to start saying interrupt, or it's going to start trying to do some weird code. Instruction 0 does need to be handled now. So let's go in here and put it in. Do just nothing in there for now, see what we get. So, oh yeah, look at that, it's printing that out in, yeah, is that correct? Which is, oh yeah, okay, yeah, that's right. So the program counter has not been set correctly. So maybe we can do maybe we can start doing our test-driven development and do the easy way. Let's do that. Let's make this test work, maybe. Let's fix it like that. Does that fit? Yeah, that totally fixes it. Now, why is that passed? Because it should have been... This hasn't consumed 7 cycles. Has it? How did that manage to pass? Oops, don't want the shifts test. That didn't... Oh, it might have consumed 7 cycles because it kept going around and doing break, maybe. Yeah, I think that's what actually happened. So weirdly, I've written enough code to make that test pass. I wasn't expecting that, but there you go. That works. So we clearly need a better test than that to make sure that this all still works. So I suppose one thing you can do is just have a different reset vector in your test. Break will load the program counter from the interrupt vector. Let's just do a second test for that. So now I can't fudge it now. I've got to do one of those tests is going to be, oh, wait a minute. Oh, that's interesting. Why is that passed? Oh, because I need to test it correctly down there. There we go. There we go. One of those has failed. So we can't make both of these ever pass now. I can't just fudge this and go, let's go for 9,000. And let's try and make it work like that, because then the other one will fail. So it's clearly, I'm not able to just fudge this anymore. So I've got to do something better than that. So let's do what it wants of us. Let's read a word from the reset vector, or the interrupt vector. And let's just give it a name. There we go. Wonder if that makes it pass. And now they both fail. So this is the thing where it starts scrolling it off without showing me the tests. Let's see why one of these failed. I think it might be failing on the cycles. Is that what it did? Ooh, actual cycles. Yeah, it took more cycles than we wanted. And that's not good. I think that's because it didn't take enough, then it went round and did it again and then took too many. So yeah, so we've basically, we might have fixed, have we fixed the program counter though at least? We fixed that one. What about this one? And the program counter is... Yeah, so we fixed the program counters, but we've created a different problem in that we're not doing the cycles correctly. So there's clearly more to be done there. So when we read a word, it's taking 2 cycles to read that. So it's taking 1 to read the instruction, 2 to read the word, that's 3. And then let's just subtract the other 4 to get us up to 7. And then when we make our test pass again, there we go. And now we're back kind of in the same boat that we're really not doing enough tests to make this sure this is working correctly, because we're not pushing the program counter and processor status onto the stack. We're not doing that part. and we're also not setting the break flag. So let's put in a test for the break flag. Break will set the break flag. Okay, let's do that. We don't care really what the reset vector is this time, because we're only going to execute this one instruction. We just care that the flag, the break flag, is false, and at the end of this the break flag should be true. Oops, did that wrong. Yep. Oh, I've called it break flag. The break flag, there we go. So we're not setting the break flag, so we need to do that. So let's make that one pass. And it's as simple as that. Right, that's another thing over. So next thing, we need to test that we can actually, we need to test that we are actually pushing stuff onto the stack, really. So we can get rid of this break test for this one. Whatever the stack pointer was before, we're expecting it to be, it will have to push on, the program counter is 2 bytes and the processor status is 1 byte. So it should be 3 bytes away from where it was before. So that's one thing we can check, that the stack pointer is equal to stack pointer minus 3. Break will change the stack pointer. Well, we'll put break will push 3 bytes onto the stack. So that's all we're really testing there. We're not actually testing that they're the correct bytes, we're just testing that they did go onto the stack. Or something went onto the stack. So yeah, that one fails. And again, we could even do the weird thing here if we could fudge this one as well. We could actually just subtract 3 from the stack pointer, and then is that going to fix it? Yeah, that's crazy. So we clearly need another test to make sure that something goes onto the stack. Is that definitely right? Program counter is 2 bytes and the status is the other 2. So let's check that we push the correct stuff onto the stack. So we don't need that particular test anymore. I'll leave it there for now. Yeah, what we could do, so this is like, we've got a copy of the CPU before. Oops, that's bad what I just did there. So what we can say is, what we're really interested in is the old stack pointer. Is that really what we want? Yeah, let's do it like that. That's the old stack pointer. Let's see that we need to push on the program counter. So I'm assuming they're going in this order as well, that the program counter is getting pushed on first and the processor status is then second. So what do we expect here? So this is the before it happened. We're expecting 3 bytes. The question is, what are the 3 bytes that we want? So there's the old stack pointer, and it'll be the old stack pointer, and then the old stack pointer minus 1, and then the old stack pointer minus 2. I'll just put a minus 0 on there just so they line up. Oh, I can't do it like that. That's wrong. It's the memory. Yeah, because that's where, oh, and of course we can't, the stack point is a byte, so we've got to, I'm going to OR it with that to turn it into its actual, oh, that's just crazy looking, isn't it? So we're actually just pulling out the actual stack addresses there. Let's just line this thing up so we can actually see it. So we're expecting something in these bytes here, but what is it we're expecting? Let's just put some zeros in there, fill that in for now. We're definitely expecting, oh, can I even do this? Oh, because I've redefined the thing. Break will push PC and PS onto the stack. Oops, stack, not state. Is that, so that compiles, I just don't know what these values are for this. So I think it should push the little endian processor program counter on. So the program counter, and that'll be the program counter after the break, will be FF01. So I assume this is going to be 01 FF, and because that's where we would return to after the interrupt. And the processor status is going to be the CPU copy processor status. So I think that is definitely failing, because there's probably just zeros on the stack there at that point. So let's see if I push now. I can't just do this here anymore. I now need to push these on, push this stuff on just here. So have I got to push byte onto stack? I have. I've got to push word onto stack. No, but I've got push program counter onto stack. That's exactly what I want to do actually. So does that take any? So I've already got a function to do that, and processor status. So I can just push byte onto stack for that. Because we've already done that before. Now I shouldn't need to do this anymore, because these 3 cycles, because those 3 things are taken up by that. And I think this is going to take another 3 cycles away. So I'm just left with this minus there, I think. And that might be the cycle that it took to write that processor status flag. I'm not exactly sure. I think that might be right. I wonder if this is going to pass. Oh, processor status, not program counter. That's the one. Right, well, what's going to happen? And that has totally failed all the tests now. So what have I done wrong there? Because the program counter, I'm changing it before, and I need to change it afterwards. After I do that, not before. Oh. Right, is that any better? No, that's actually the same. So what did we get? Oh, I've actually taken an extra cycle. So I didn't need this. So why is that? It's 1 to read the instruction, and there's 2 in there. That's 3. Pushing a byte on the stack is 4. Reading a word is 5, 6. And I think this is supposed to be 7. So how have I managed to get to 8 there? Is there something in here? Oh, wait a minute. Read word is 2. So it's 1 for the instruction, 2, 3, 4, 5, 6. No, that is right. Where's this extra cycle coming from? Let me just have a quick double check. So yeah, so it goes in there. It's taken 1. It took 2 in there. This should take 1. It took 2. Why does that take 2? What's going on there? Is that supposed to happen like that? Because we do take 2 in there. Oh, because you have to decrement the stack pointer. So that takes an extra cycle. Right, that makes sense. Okay, so it all comes out in the wash, and we don't need this here. This must somehow be free in the processor, or at least it was in the 6502. Let's see what we get from that. And the answer is nothing. Wait a minute. no, we've still got something wrong here. So it looks like I've got these maybe backwards. So we are getting, I'm expecting one, so least significant byte, most significant byte, but maybe we store those in the opposite order. I'm not actually sure. That could actually be wrong. As in, I think it's supposed to, I mean, when you're storing the stuff in little endian, when you're pushing it on the stack but you're going negative, do you store the little byte first and then you store the bigger byte, which would be what I'm checking here. And actually I've got, it came out at the FF was in that byte and what's going on in this one? And this one's got 0 in it. That doesn't seem right at all. So let's debug this one. Let's just see what's going on in there. Thought this was going to be reasonably easy, but maybe not. We are going to push the program counter onto the stack. Now the program counter is, what is the program counter? It is currently FF01. So we're going to push it on, we're going to write a word. Oh, we pushed the program counter. Yeah, we push the program counter -1 onto the stack when we do this. Not the program, that's where that 0 came from. Actually, it's also in the opposite order. So it's come out in the opposite order, but it's also the program counter. Now, it doesn't say that it pushes the program counter -1 stack. This pushes the program counter onto the stack. And that would make sense because after you come back from the interrupt, you want to be in that exact place, I think. I think that's correct. So I think this is where this is wrong, and I need to do, yeah, so that pushes PC -1. See, I might rename this then. Let's just call it that. Let's just see what that breaks. So JSR does push PC -1 onto the stack. Oh, -1. Alright, okay. Is there another one of these somewhere? Alright, and that's this one. So we don't want, so in this case we actually want to push PC -1 on the stack and push PC onto the stack. So in this case it will be just that. Now we should, I think this is, think this is still going to fail because, yeah, we've got the right bytes, but they're now in the wrong order. And I'm wondering if I don't know what the actual correct order for this is now, because I know little endian is like the little byte goes first. But in the case of the stack, is that how it works? Because if that's the case, both these functions are wrong. But we clearly didn't have a good enough test for the other one, because if we pushed it on in the wrong order and then popped it back in the wrong order, it would still work fine. It wouldn't be correct emulation, but it would still just work as long as you did it the same both ways. So I don't know. I mean, if you were storing a byte little endian, then you store the little one first, and that would be the opposite way around. But because the stack goes, like, it goes down, I don't know exactly how that works. I wonder if I could find out. Okay, so this Stack Overflow page is claiming that when you push on, because I'm looking at JSR instruction, because that's the other thing that we've got that does push the program counter onto the stack, and it is saying JSR pushes the instruction last byte. The high byte is pushed first. Now that might make sense, because if you did push the high byte first, which would end up being this, that would mean that if you read this from here, this would be little endian, because you are actually storing, maybe it's better if I write this backwards like this, and it kind of makes more sense that as you go upwards in memory, you're actually doing the low byte then the high byte. So yeah, but I think I'll write it the other way around. But yeah, according to this basically says that the high byte, which is the FF there, is pushed first and the low byte is pushed second. So in effect, I think that means that we've got this right, and that is a pass. So, I mean, we could be wrong on this. This page could be wrong. It could be nonsense. We really need to check this on an actual, if we actually run a program on it or a test program, which is what I want to do next, actually, after we've done all the instructions. Because it's definitely worth noting that there are things you can get wrong in here. For instance, if I just change the break instruction to, I don't know what instructions we haven't used here, 0, 1, something like that. This will still work. Oh, case 1's already used. If I can change it to something that hasn't already been used, there you go. It still passes. So it's definitely possible to put errors into this program and still get passing tests, which really, if you compiled your own program, the break command would not come out 2, it'd come out 0, and that would work then, or it would fail your program. So we still need to do extra testing later on. But is there any more tests that I need to do for the break command? We've tested that the program counter and processor status are on the stack. We've read the value from the interrupt vector. We tested that. We tested that that got into the program counter afterwards, and the break flag got set to 1. We tested that as well, didn't we? Break flag there was false, it got set to 1. So I think that's break command working, I would say. And in the end, it wasn't actually, because it hasn't got any addressing modes, it actually makes it a bit easier than normal. Yeah, except we just had to do that push PC to stack and then push PC -1 to stack. I mean, maybe we can rewrite this the way it's supposed to be. We do write byte. Or is it easier to do it like this? Maybe I'll just refactor this now it's working actually. So we want to push the low byte of the program counter first. So that's the low byte. And now we can just push it in at that exact place. And then we decrement the stack pointer. Whoop. And then we do the same thing again with the high byte. So we can do that just by shifting right by 8, I think. So that's another way of writing that. That's like the way it's kind of described, as it's you do the high byte, then you do the low byte. So in fact, that doesn't really change anything. Oh, except it did. Sorry. Oh, you do the high byte, then you do the low byte. And there it is. That doesn't actually change anything. So we could do the same thing on this one, except it's in fact, let's refactor this just a little bit more. Let's take this and we'll do push word to stack, and we'll have a word value. There we go. How about that? And now we can just call this. So that pushes the program counter. Is that right? Oh, let's put this above here. What have I done wrong here? Let's Let's do it like that. And this one pushes the program counter -1 onto the stack. Just so we give those, oh, that's program counter. Right, so that's just refactored pushing a word onto the stack. Yeah, and that doesn't really change anything. So we're just not rewriting that weird bit of code twice, but we've written it more explicitly, like how the processor would actually do it. Yeah, written it, then decremented it, written it, then decremented it. So that makes sense, and it takes the same number of cycles because it's just taking one to do it. So I'm quite happy with that. So I think maybe now we can move on to doing return from interrupt. It's used at the end of the interrupt process chain. It pulls the process flags from the stack, followed by the program counter. Yeah, that makes sense because that was the opposite of the order we popped them on. We set all those from the stack, and then we set the program counter. So let's do our first test for that. So I suppose we need to, we're going to have to do a break, but we know break's working now because we tested that. So we want to do a break to a specific place, which gets loaded from the interrupt vector. So this is, we're going to go to 8000 again. So 8000 is the address we will jump to, and then at 8000 we're going to put an RTI, return from interrupt. And this is an odd one because we expect 7 cycles for the break and 6 cycles to return from the interrupt. Do we need the old stack pointer? Maybe not. Let's get rid of some of these. So what do we expect? We expect nothing to change. So we expect the stack pointer to be back where it was, because we've popped everything off the stack that we put on it. We're expecting the program counter to be back where it was, because we're back where we were. And we're expecting the processor status to be back the way it was, because we've removed it. And we overwrote our break command that we set when we were in there. So in theory, RTI can return from an interrupt with, I suppose it's leaving the CPU in the state that when it entered. There we go, it's a bit of a long title, but it's explicit. And put this in. It's instruction 40. This could be the last instruction. I think that might have been the last instruction that we're testing. And there we go, it wasn't handled. So let's go and put that one in. Let's just check that we're getting lots of wrongness here. Process status is wrong, program counter is wrong, stack pointer is wrong, number of cycles is wrong. Cool. So we want to pop the processor, pop a byte from the stack. We've got a function for that. It's good when you get this far into a program and you've got loads of functions that already do everything. You don't really have to write many things because you're getting towards the state where you've got it. We pop a byte from the stack. That is going to be the processor status. So let's just see that we got that to work. The processor status is, ooh, that's not right. I would have expected at least that to have worked. This one. Oh, because we're not executing the right number of cycles. I think it's gone round and it's maybe changed the processor status by doing something weird. So maybe we'll have to write the rest of this before we can really understand if that's working. Because we've consumed 18 cycles. And we should have only consumed, so 13. So we expected 13, but we actually consumed 18. So we didn't consume enough on this one, I think. I think that's part of the problem. So I wonder if we could just get that to work for now. Cycles minus, it's going to pop a byte, that's going to take 1. We need to take, and it's done 1 from the instruction, so we need to take 4 more. This is kind of what we did in the last one. I'm just trying to get one thing to work. The processor status, yeah. Oh, did I have that wrong before? Was I reading PC instead of PS? So, let's see that, please. Oh no, yeah, that did kind of change something. So, I'm not getting this right. Oh, it only needs 6, so that's 1, 2, it's 3 to pop a byte from stack, so it's 3. Right, I forget because it's got to decrement the stack pointer. Okay. Oh, it still took 14 cycles. Well, let's deduct another one off there. Just want to get that so it just runs just the code I want. Okay. So processor status is working correctly. It is getting that value off the stack now. So what's the next thing? The program counter. We need to pop that afterwards. So have we got a pop word from stack? We have. And that is the program counter. Okay. I imagine I don't need this anymore. I wonder if that's fixed everything. Nope. Because the cycles is still wrong. Taking an extra 1 now. This might be where my whole thing about putting the cycles in has really made a mess of things, maybe. Yeah, that's a point. Program counter should be the instruction after the break. Yep. Because basically we execute the break, which takes us to FF01, and then we push on the program counter at that point. So actually I expect the program counter at the end to be this. Oh. Which is the instruction after the break. So we just continue where we left off after the break. I think that's right. Let's try that. Oh, okay. So that is correct. But we're consuming an extra cycle, which is really unfortunate. This is going to be like the one instruction at the end that really actually makes a mess of things for me. 6 and 7 to do that. The question is that I suppose this is the problem with testing 2 of these things at once, is it's really hard to tell. I suppose what I could do is I can execute what I think is, let's do it this way, and then we can really be sure what's going on. Expected cycles for break 7, expected cycles for RTI is 6, and then we can actually execute these like this. So we do the break and then we'll execute the RTI. And then we'll really be sure that it was that's wrong. So we're just testing the, testing the cycle counts individually. Is that right? Yeah, so it is the RTI that's taking 7 and it should take 6. So I've just refined the test a little bit to make that a bit more clear that we are taking the wrong number of cycles. And actually it's a bit better for me now because now I can actually step in there and I can actually just execute the RTI part. I think this cycles thing was going so well until the last instruction. So we have consumed 1 to fetch the byte. Pop a byte from the stack. Took 3. Is that right? Yeah, it took 3, so that's 4. And then pop in a word. Oh, what happened there? because I went through and number of cycles used 7. What did I do wrong? Oh yeah, because sorry, yeah, it wrapped round because it took 7. So why did it take 7? That takes 1. Popping byte from the stack. Apparently takes 3 cycles, does it? This could be the bit that's wrong here. I'm not sure that that's right. Because we pop a byte from the stack, it's probably 1 to actually read the value. It's 1 to change the counter, the stack pointer. I don't think that it's right to consume 3 cycles from that. I don't believe that it is. I think that could be where I'm going wrong. I think it's this. So it consumes a cycle for doing the stack pointer, and then it consumes another one for reading the word from memory. I think that's going to fix that test and then break another. Oop. It broke quite a few actually. But it did fix that test. So what have we got? PI can pull a value from the stack and into a register. Stack operations test. So let's go have a look at that. So I don't know if what I'm done here is right, but it does seem wrong that popping a byte from the stack takes 3 cycles. Stack operations test. So now we're going to go look at an old test. So this is the one, just checking that this is the one that actually, is that the one? Ooh, yeah, went round to 10, it should have been 4. So this is the one that is definitely the first one that's screwed up by that change that I just made. So let's see, so we expect 4 for this. So what do we got? I have to go back and look at what this instruction does in a minute. 1 to read the byte, it's always 1 to read the byte. So this is PLA, is that, that's PLA again. Pull accumulator from stack. Pulls an 8-bit value from the stack into the accumulator. So we're going to pop a byte from the stack, that's going to be 2. Oops. And there's still 1 spare cycle there. So yeah, I still don't think it's right that takes 3, popping a byte from the stack. 1 to decrement the, unless it's 1 to like decrement the stack. No, I don't think that's right. It'll be 1 to decrement the stack, 1 to read the byte. I don't know. I feel like an extra cycle is being consumed in there, and I don't know how that's happening. Nope. Where are we? So, I mean, I'm fixing it, but at least I'm taking the right number of cycles. I don't know if I'm doing it in a correct way, like for what the processor would be doing, but I think this is correct. This website doesn't really tell me how cycles are consumed because it's internal to the processor, so I don't actually know. So let's try that one, PLP. It's in here. So this is the same problem, I think. It's going to be 1. Where are we? 1 to do that, and then 2, 3, and it should be 4. So yeah, it feels like there's another one there for some reason. I don't know why that would be. Is it because it's 1 to write the processor status? Maybe, I don't know. Don't know. That's the answer to that. But, oops, but I have, there we go. But what we do have is a full suite of tests that we think test this 6502 emulator and are actually keeping the cycles. At least we know they're correct once it comes out of one function. We don't know if they're correct kind of internally. That is, I believe, unless I've missed some out, every single instruction implemented, and I've written 302 tests to do it. So You probably need more tests than that to get this fully working, but I think that's a pretty good start. I don't think I need to do another test for return from interrupt because I think we've tested everything in that. Yeah, so that's all good. So we are, I suppose you could say at this point we're done, but I'm going to go out on a limb and I'm going to say we're not, because what we need to do next is actually run a program. And I have been looking for some test programs, and I've already had a quick go actually at running one of them before this processor was finished, and I can tell you that it did fail. So what I'm going to do, I'll show you. So I found there's this GitHub page from this guy, Klaus2M5, who has written basically a giant program. This is it here. It's just a giant program that runs from top to bottom, and it tries to test every single, I think he says it tests all opcodes of the 6502 emulator using all addressing modes with the proper focus on setting process status and register bits. And it does appear to have been updated reasonably recently, 10 months ago. So that's pretty good. And it actually comes, the problem with when you get these programs is that you have to be compiled with a specific like compiler or assembler in this case, because the way it formats things might be specific to that. So this one has actually got, it's got the actual assembler in here because I don't know where else it is, but there it is. It's actually right there in that zip file. So next video, we will compile this, try and get it to run, and then see if we can find any more problems or see if this emulator is working in any respect at all. And see if we can, if it does get to actually, when it does fail, because I know one of the tests is failing, but it might be fixed now, who knows? Then we'll see if we can add more unit tests to try and fix it. But at the moment, I'm pretty confident we've got a lot of stuff working, but that on its own isn't enough to assume that it's all working. So that'll be the next thing to do. And we haven't implemented decimal mode, but I believe you can exclude that from this test, disable decimal. So we can disable the decimal mode for now and test everything else but that, and run this giant program and see if we can actually get any kind of results out of this. So that'll be the acid test is next, and we're going to see, or the smoke test. We'll put it through this and see what blows up. So it could be a short video in the next one if it all just works, but it could be the next lot of hell to get this working. But I'll catch you for that in the next one.